All right, let's try one that's a little bit more going on. So we're given a function here, and we're gonna find the absolute maximum and minimum values of that function. So in this case, it's f of x equal to x raised to the 1/3 power times 5 minus x. And we're gonna do this on the interval where x is greater than or equal to -8, but less than or equal to +1. All right, so first thing we need to check is, does the extreme value theorem apply? Are we guaranteed to have an absolute max and absolute min? And what that means is our function continuous? Are we dealing with a closed interval? All right, so, and the answer is yes to both of these. So we just kind of state this out. F is continuous product of a root function. That's what this x raised to the 1/3 power is. That's just a root function. And the cube root is continuous for all real numbers. And then we have 5 minus x here, which is a polynomial, so that's continuous for all real numbers. And so when we multiply two continuous functions together, the result is continuous. So f here is the continuous product of a root function and a polynomial. So it's guaranteed to be continuous. And we're talking about the closed interval. -8 to 1, where we're using those square brackets to indicate that those endpoints are included, and we can see that the endpoints are included because these are less than or equal to signs. So x is less than or equal to -8. The equals means we're including -8 in our considerations. Same thing with x less than or equal to 1. We're including the possibility that x is equal to 1. So we're including the endpoints. So it's a closed interval. All right, so nice. Function f here is a continuous function. We're dealing with a closed interval. So the extreme value theorem guarantees this function will have an absolute max and an absolute min on that interval. Now we need to start looking. So the next step is we want to find our critical numbers. And to do this, we need our derivative. So remember, the critical numbers are where the derivative is 0 and where the derivative is undefined. So we need to figure out our derivative. So let's calculate. And one kind of key word here is this was a product. We identified that it was a product here. So in order to do the derivative, we got to use product rule. So let's apply the product rule. So we write down 2 copies of our product. X raised to the 1/3 times 5 minus x, and then a second copy, x raised to the 1/3 times 5 minus x. In the first copy, we apply the derivative to the first part. In the second copy, we apply it to the second part. And then for product rule, we put a plus sign there in the middle. So that is our product rule. All right. So now we keep differentiating. So differentiating this root function, we get 1/3 x raised to the -2/3 power times 5 minus x. And then differentiating 5 minus x, we get -1. All right. So if this was just a problem for finding the derivative, that would be fine. But now we actually have to do something with the derivative. We have to figure out where it's 0. We have to figure out where it's undefined. That takes a bit of work. So we want to try to simplify this down as much as possible to kind of help us figure out where the derivative is 0 and where it's undefined. All right, so what can we do? Well, I see a negative exponent here. It's normally helpful to write that back as a fraction. So let's see what we get. So I'm going to rewrite this. Well, maybe I'll do it over here. I'm going to rewrite this as a fraction, and I'll put the 3 with it. So we're going to get 5 minus x on the top, and then 3 times x raised to the positive 2/3 on the bottom. So I've just rewritten this first part as a single fraction. And then we have minus x raised to the 1/3 power. All right, so that's not too bad. That's a little better, but we want to try to get this as simple as possible. And a lot of times when we have two separate terms here, and one of them's a fraction, we want to try to combine them into one single fraction. And so what we're going to do is we're going to do that. We're going to get a common denominator. And you can think of this second term here as just being a fraction over 1. So our common denominator is just going to be this 3 times x raised to the 2/3 power. So we're going to multiply this second piece over here by 3 times x raised to the 2/3 power. Just form a fraction with that. And so if we simplify, we're going to have 5 minus x over 3x raised to the 2/3 power. Nothing happens there. But in the second piece here, we're going to have minus 3x to the 2/3 power in the denominator. But what are we going to have in the numerator? Well, we have x raised to the 1/3. We have x raised to the 2/3, and we're multiplying those together. So we add the exponents. So 1/3 plus 2/3 is 1. So we end up with just a 3x over here. Okay. Now we have the same denominator, so we can actually combine these now into one single fraction. So 5 minus x minus 3x all over 3x raised to the 2/3 power. And if we clean that up just a little bit more, we get 5 minus 4x over 3x raised to the 2/3 power. And that's a nice form for our derivative to work with. And so we want to figure out, all right, we have this nice simplified derivative. We want to figure out, well, where is the derivative 0? And where is the derivative undefined? And when we work with a fraction, the way a fraction can be 0 is if the numerator is 0. And when we work with the fraction, the way a fraction is undefined, normally for these functional terms here, the way a fraction is undefined is if we divide by 0. So if our denominator is equal to 0. So that's what we're going to look at. We have this function here, and in order to find where the derivative is 0, we're going to just look at the numerator. And in order to figure out where the derivative is undefined, we're going to look at the denominator. So if we do that, we get 5 minus 4x. We set that equal to 0. And if we solve that for x, we get x is equal to 5 over 4. Okay. Not too bad. Now what about for where our derivative is undefined? So now we're going to set just the denominator equal to 0. So we get 3x raised to the 2/3 power equal to 0. And the only way this is true is if x is equal to 0. So we actually get two critical numbers for our function, x equal to 5 over 4 and x equal to 0. So these are the critical numbers of function f. There we go, x equal to 5 over 4, x equal to 0. But we want to keep in the back of our mind, we're talking about our function just on this closed interval. So if we didn't have this closed interval in mind, then yeah, x equals 5 over 4 and x equals 0 are both critical numbers for our function. First of all, our function is defined at both of those numbers. But for the purposes of this problem, we're only interested in the x values between -8 and 1. And unfortunately, 5/4 doesn't fit that description. It's a little bit bigger than 1. So we're just going to use x equals 0 in our considerations. So yeah, 5/4 is a critical number for our function, just our function. But in the context of this problem where we actually have this closed interval, we're only going to use the number that's actually inside the interval, which is 0. All right, so far what we've done took a little bit of work to get here, but we first just identified that our function's continuous on a closed interval. Next step, we found the critical numbers. So this meant find the derivative. And a lot of our work here was first calculating the derivative and then simplifying it down. And, as soon as you start seeing negative exponents or you have fractions, normally our strategy is just to try and consolidate it all into one single fraction here. And once we have this single fraction, then the way we find the critical numbers, we need to look where our derivative is 0. So we set the numerator of our fraction equal to 0. And then we also need to figure out where our derivative is undefined. And when we have a nice single fraction like this, we just set the denominator equal to 0. And that gives us two equations, which we can go on and solve. And then finally, we're only going to use the critical number or critical numbers that are inside the interval. All right, so the next step is we go on and evaluate. So we have our endpoints here, and we have we're only going to use one critical number. So we're going to plug 0, we're going to plug 1, and we're going to plug -8 into our function. So here's our critical numbers. And then here's the endpoints. And again, x equal to 5/4 is a perfectly good number, perfectly good critical number. It's just not inside this interval, so we're not going to worry about evaluating it here. All right, let's see what we get. So let's plug 0 in. We get 0 raised to the 1/3 power times 5 minus 0. That's just 0. Let's plug 1 in, and we're plugging into the original function. So yeah, we had our derivative from before, but once we get our critical numbers, we're kind of done with that derivative for this closed interval method. So our evaluating here, where we're evaluating, we're plugging into the original function. If we plug 1 in, we get 1 raised to the 1/3 power times 5 minus 1, which is 4. And then when we plug in -8, we get -8 raised to the 1/3 power times 5 minus -8. And this ends up being, well, -8 raised to the 1/3 power is -2. And then this is positive 13. So this is negative 26. Make sure we get that right. Yes. So 5 minus, be careful these double negatives. So it's 5 minus x, and we're plugging in -8. So it's 5 minus -8, that's positive 13. And then -8 raised to the 1/3 power is -2. So -2 times 13 is -26. All right, so that's our evaluation step. And now we need to actually go through and compare. So we have these 3 values that we're going to compare. The largest is our maximum. The smallest is our minimum. And we see that 4 is the largest value there, and -26 is the smallest. So here's our absolute max, and here's our absolute min. Again, could happen at any of these, so it's just kind of coincidental in this example that the absolute max and min, again, are occurring at the endpoints. But you might find one where it occurs at a critical point, a critical number. So let's just go through then and just formally state our result. The absolute max value, the value of our function, is 4, and that occurs at x equals 1. And the absolute min value is negative 26, and that occurs at x equals negative 8. And because it's important enough, let's just make note. X equals 5 over 4 is technically a critical number of this function, but it's outside the interval. And that's why we didn't evaluate at that x value, 5 over 4. Yeah, it's a critical number, just outside the interval. So just important enough to, let's just note that here. It's outside the interval, so we didn't include it in our considerations. All right. So this gives us a nice, this closed interval method gives us a nice kind of strategy for how to locate where a function has an absolute max and an absolute min on a closed interval. So again, the steps: first, identify that the function's continuous and you're working with a closed interval. That guarantees you're going to have a absolute max and an absolute min by the extreme value theorem. Then you start looking for where it happens. So we find our critical numbers, which means get the derivative, simplify the derivative, and then figure out where the derivative is 0 and undefined. Then we take our critical numbers and we take the endpoints of our interval and we plug them into our function, and we throw out any critical numbers that are not inside the interval. And by plugging into the original function, this gives us a list of values that we go through and compare. And the largest value is the max, and the smallest value is the min. And there we go. That's the closed interval method. So we're going to be playing this sort of game quite a bit, of locating maxes and mins and identifying where the critical numbers of a function occur. So there's going to be a lot of these little techniques and strategies that we're seeing here and definitions are going to show up over the next few lessons. All right, so we'll see you then. Bye-bye.